So before moving on, dear students, before moving on to the experiments related to 5-5 timer, I will just brief out what is 5-5 timer. The 555 timer is commonly used IC designed to produce a variety of output waveforms with the addition of an external RC circuit. You see here you have a IC. So the internal block diagram is being given, and this IC is nothing but you can have a variety of output waveforms with the addition of external RC circuit. So it is the 5-5 timer chip is extremely robust, and it is a stable 8-pin device that can be operated either as a very accurate monostable, bistable or a stable multivibrator to produce a variety of applications. The basic 5-5 timer gets its name from the fact that there are three internally connected 5 kilo ohm resistors which is used to generate two comparator reference voltages. So you can see here the three 5 kilo ohm resistors. So they are driving a comparator. So here this is a VCC supply. So the voltage gets divided at this point as 2 by 3 times of the VCC, and at this point as 1 by 3 times of VCC. That becomes a reference voltage for the comparator. The single 5-5 timer chip in its basic form is a bipolar 8-pin mini dual inline package, that is DIP device, consisting of some 25 transistors, 2 diodes and about 16 resistors arranged to form two comparators. So I have here the simplified block diagram representing the internal circuitry of 5-5 timer. So the circuit is as shown here. And the pin number 1, that is ground, the ground pin connects the 5-5 timer to the negative supply, that is it is grounded, and the second pin, the negative input to this comparator. If I give a negative input to this comparator, that which voltage is below 1 by 3 VCC, because this point is the reference voltage 1 by 3 VCC, and if the voltage across pin number 2 is less than that, then this comparator gets triggered, that is set is triggered, and Q becomes 1 and Q bar becomes 0, and the base of this transistor becomes 0. The output will be the ground point, this will be grounded, and the Q bar, if it is 0, the output will be 1, because the output driver consists of an inverter. So pin number 3, the output pin can drive any TTL circuit. The output of this can drive any TTL circuit and is capable of sourcing or sinking up to 200 milliamperes of current at an output voltage equal to approximately minus 1.5 volts to small speakers. Next, coming to the pin number 4, that is reset pin. This pin is used to reset the internal flip-flop controlling the state of the output. So you can see the pin number 4 is connected to the Q and Q of the SR flip-flop. This is an active low input and is generally connected to a logic 1 level when not used to prevent any unwanted resetting. Next is the control voltage, pin number 5, control voltage. This pin controls the timing of the 555 by overriding 2 by 3 VCC level of the voltage divider network. So when you have a control voltage at this point, this overrides. If I want to, this point is at 2 by 3 VCC level, and if I want to if I provide a control voltage greater than that, this comparator gets triggered, and it helps in finding out the RC timing circuit. Pin number 6, that is threshold, the positive input to the comparator number 2. So the positive input to the comparator. So this pin is used to reset the flip-flop when the voltage applied to it. If the voltage applied to this exceeds 2 by 3 VCC, the output is positive and the reset pin is triggered. And reset pin is triggered, that means you are exceeding when it is 2 by 3, causing the output to switch from high to low state. This pin connects directly to the RC timing circuit. Next pin is the discharge pin, and here the discharge pin is connected directly to the collector of an internal NPN, you can see here, and which is used to discharge the timing capacitor to the ground when the output at pin number 3 switches low. When this is at low point, that means this is at high point, that is internal driver, and this helps the output at pin number 3 to that is switch the discharging capacitor to discharge into the ground. Pin number 8, this is the supply voltage. This power supply pin and for general purpose TTL 55 timer is usually between 4.5 volts to 15 volts, and generally use VCC 5 volts or 12 volts will be using in the laboratory. So this is about the internal block diagram. The same block diagram has been shown here with again external reset pin here with the Q2 and output voltage. The output stage consists of inverter. You can see 5 by 5K 5K here. This is 1 by 3 and this point is 2 by 3. If I want to operate this comparator, the threshold has to be given greater than 2 by 3 VCC. And here if I want to trigger this comparator to at the triggering point, I should have a negative impulse which is less than the magnitude. If I say it should be less than 1 by 3 VCC. Okay, the same internal, this is the same internal block diagram. So if I connect a circuit, extra circuits, external circuits R and C to these points, I'll get in the three type of operations I can have. One is monostable, stable, and the bistable operations. So here the monostable operation, I'm explaining about the monostable operation. So here I have pin and 7, 6 are shorted, and we have a resistor between 8 and 7 and another resistor across R2. And the timing T is equal to 1.1 into R1 into C1. This is your R1 and this is your C1. So you can see whenever, how does this operate in a waveform. When you are applying a triggering pulse at pin number 2, and when the triggering pulse reaches that 1 by 3 point, the VCC, then your capacitor charged, the capacitor starts charging, and when it reaches 2 by 3 times of VCC, then the upper comparator is triggered and the output goes in discharges the capacitor to 0, and you have the pulse with the charging of the signal. During that you have a on period, and this continues to be in the until another triggering pulse comes. You will have the voltage of the across the capacitor will be 0 until another triggering pulse comes, and then that makes the capacitor to charge. So this is the monostable. And in the stable mode, we don't require we set such that the charging and discharging of the capacitor is between 2 by 3 VCC and 1 by 3 VCC, so that the second comparator is not set. It is between 2 by 3 and 1 by 3 VCC. So here this is the circuit diagram. When a negative pulse is applied to the triggering input, when I give a triggering pulse here at the pin number 2, the internal comparator, that is comparator, detects this input and sets the states of the flip-flop, changing the output from low state to the high state. So when I have this one, so from low state to high state, it is triggered because when the output goes below 1 by 3 VCC, the second comparator gets triggered, and it sets that flip-flop, changing the output from low state to the high state. This action in turn off the discharge transistor connected to pin number 7. So we had seen a discharging capacitor Q1. So this turns off when this is at high, this is 0, this point is 0, and automatically Q1 turns off, and thereby removing the short circuit across the external timing diagram. So when it is off, this point, that is this, is not shorted. If this is on, the R does not come into account. This becomes another part, that is you are bifurcating this R. So this action in terms of the discharge transistor, as I told you, and this action allows the timing capacitor to start to charge up through the resistor R1, the through resistor R1, it starts charging, and when it reaches 2 by 3 VCC, when it reaches start charging when it reaches 2 by 3 VCC set up by the internal voltage divider network. At this point, the comparator's output goes high and resets the flip-flop back to its original. So you had so here again it resets the flip-flop. At this point, the capacitor charges to the higher value 2 by 3 VCC. The comparator 1 gets initiated and the output goes high and results the flip-flop back to its original state, which in turns on the transistor and discharges the capacitor to ground through pin number 7. So you have the monostable circuit that triggers on negative going pulse applied to pin number 2 here. So the same thing, this can be explained according to the circuit diagram. So here you had you have a negative pulse. So in the circuit, this negative going pulse, we can take it directly from a pulse generator, or you can have another external circuit that can be applied, which will be giving you a negative going pulse. So this is how we are having whenever here the from negative state, that is off period, is always the stable state, and when from the stable state we are going to unstable state, and this unstable state remains until the capacitor is charged to 2 by 3 VCC. Once it's charged to 2 by 3 VCC, again the comparator 1 is activated and you come back to your original stable state. So the state 1 is an unstable state and state 0 is a stable state. So you have a one single stable state, that is monostable. Next, if I moving on to the circuit diagram. Here I have a circuit diagram using a multisim, the same circuit diagram I'm using. This is the circuit diagram, that is you have this extra diode and one extra resistor, so that these pulses are equal in nature. They are square wave type of pulses. So you want to make the duration of the pulse to be of smaller values. So we are using this capacitor which can charge from 10 kilo ohm and discharge it whenever this is diode is hot bias. You have a short circuit path, so you have a small pulse generated through this squared pulses. So you have a pulses which is of this nature, very small pulse duration. Otherwise, you have this pulses as in this manner. So we are using a capacitor and this part, so that when this is when this diode is forward bias, you have a short path. So this resistor doesn't come into account. And when this is reverse bias, you have the capacitor charging through this resistor R. So that is how do you design it? The design depends on your equation where T equals 1.1 R1 C1. Assume C1 and calculate R1 for a given T. So coming to multisim, how do you generate a develop a circuit using multisim? So you know how to do the connections. So I have a 5 timer taken and I have the circuit connected. You have R1, R2, C3 and the pulse is taken. The circuit is connected according to the circuit what is being shown here. The same circuit has been connected using a multisim operation. And then if I now run this circuit, one channel of the oscilloscope, I'm connecting it to the output, and another channel of the oscilloscope I'm connecting to observe the charging and discharging characteristics of this capacitor C2. So if I just run this one, see here what is the output I'm getting. stop with this. Mm, You can see here, this is the charging and discharging of a capacitor. I will just measure the output. Just measure from this point to this point, what is the T cap? That it was a duty cycle for that is it was designed for 1 kilo hertz. So you have T equals 1 millisecond. So you can see T2 minus T1 as 1 millisecond. And you have the charging of the capacitor. You can observe here. This point is approximately from this end. The height of this capacitor charging is approximately that is 2 by 3 VCC. You can observe I have taken the scale as 2 volts per division. So this is 2 volts and this is the half of that. So 2 and 3 volts. So we have connected what 2 by 3 into voltage given was 5 volts. So 10 by 3, 3.33 volts. So it will be approximately this point will be that. You can measure that. And next the pulses that have been given was 5 volts. You can see this is 2 volts and this is 2 volts, 4 volts, and this is the half of the box, that is 5 volts. So you have this is 0 to VCC and the capacitor voltage is 0 to 2 by 3 VCC. This is the pulse output of a monostable multivibrator. You can observe the VCC is 5 volts and you can observe this. This is 3.3. The voltage at this point is 3.3. And for B in this channel A it is 5 volts, right? And the time period, that is for a waveform, what is the time period? 1.193. If I exactly place it, if I place it here now, if I want to know the time period, it is 1 millisecond. And this is the output of a multivibrator, that is monostable multivibrator using a multisim experiment, using multisim. So here in monostable you don't have the options of symmetrical and asymmetrical. It comes into account when we are doing an unstable multivibrator. So thank you, students. So in the next video, I'll show you how to design a monostable multivibrator using a discrete component. So that will be shown in your for the next video. The design part remains same for the discrete, and even the circuit diagram also same circuit diagram I will be using for the discrete also. Thank you.